Hi everyone, it's Mrs. Meehan, and in this lesson I'm going to go over some problem solving techniques when you're faced with a word problem using a combination of kinematics equations. As a quick do now, if you were provided the following variables in a word problem, which kinematics equation would you use to solve for initial velocity? So the variables that you are given would include final position, initial position, acceleration, and final velocity. So if you knew these variables and you had to solve for initial velocity, which equation would you use? Okay, so hopefully you chose what we've been calling the third kinematics equation, which is also known as the velocity position equation. So that one is the final velocity equals initial velocity plus 2 times acceleration times final position minus initial position. So in this equation, you can see that we have the variable we're trying to solve for. We have initial velocity there. We have final position present. We have initial position present, acceleration, and final velocity. So an important part of problem solving, especially from this point forward, is to make sure that you list what you know based on what you're told through the word problem and identifying what you don't know. So at a minimum, you definitely want to do that as a first step and then take a look at those variables combined and compare it to the kinematics equations that we've learned so you can select the correct one. Once you do that, you want to cancel out anything that is equal to 0 and then rearrange the equation to solve for the unknown. In this case, you would want to solve this equation for initial velocity. So as a total, there's 4 equations for motion for constant acceleration, and each require a different set of quantities. So it's basically this combination of 4 equations that you'll be evaluating to solve the different problems. If you looked at it in terms of, let's say you made a table to organize this information, it would look kind of like this. So if you could use this to compare the equations and see what different combinations they have in terms of the different variables. So here we see the first kinematics equation and the variables included in it compared to the second kinematics equation, the position time equation, and the variables included, and then the third kinematics equation. So you'll notice that first kinematics equation doesn't take into account anything about position. So if you're given a problem and you need to solve for any of these variables and nothing is mentioned about the position of an object, that kind of points towards using this equation. As opposed to the second equation, you don't necessarily need to know final velocity for this one. And then the third equation, you don't need to know time to solve the problem. So in that case, you would be using the third equation. So as a general rule of thumb, you can see that x, which is position, and t, time, are the most helpful variables to look at. Not every equation has position or time within it. So if your list of variables has time, but not position, use the first equation. If your list of variables has position, but not time, use the last equation, the third kinematics equation here. If your list of variables has position and not time, or has position and time, use the middle equation. So if you see both position and time, then use the middle equation, the second one. Now, since final velocity and initial velocity can be confused at times, it is safer to look at position and time when choosing an equation. Now, something else you might see in the word problems, you'll see the term constant velocity. This will always mean that acceleration equals 0, since acceleration is a change in velocity over time. If you have a constant velocity, that means it's not changing over time. Therefore, that would be a 0 acceleration. Now, constant acceleration is a trick. All of our problems so far have constant acceleration, so this doesn't really help you. So in the future, you will see problems where the acceleration is not constant, but for now, constant acceleration doesn't really give you any important information, so just don't get confused by that. Let's try a sample problem here. So let's say somebody stomps on a stomp rocket and they send it into the air so that it returns to the ground in 3.2 seconds. What was the stomp rocket's initial velocity and its maximum height? So the first step, read the problem carefully, draw a sketch if necessary. In this case, sometimes a sketch is helpful just to help you visualize, okay, we have the rocket here. It's going to be launched upwards, reach a peak, an apex, and then return back to the ground. From the sketch, you can see that the rocket's velocity at the apex is 0. That's always a known value when an object is at the top of its motion. If it's launched upwards, that velocity at that point is 0. Now, we don't know the velocity of the rocket when it hits the ground. So our final location that we'll consider in this problem will be the apex, because we do know that value. Down here, we don't know that value. So we're going to focus on this value. The time to the apex is going to be half the time it takes for the total trip. So in the problem, it tells you that this entire trip takes 3.2 seconds. But since we're going to focus on solving the problem up to this point, we can still answer the question by doing that. We need to have time. So it takes half the time to reach the apex. So when you do that, then you get 1.6 seconds. And then, as always, when you're thinking about vertical motion, the acceleration due to gravity applies, which would be negative 9.8 meters per second squared. So the constant value itself is 9.8 meters per second squared, but it's acting downwards. So you want to include that negative symbol, since acceleration is a vector, to indicate that. Once you've done that, now notice that this is shaded to the right. So we're kind of just focusing on the first half of the rocket's journey. We can still solve this problem with that information. You list the given variables. So also list any appropriate constants and the variable you are solving for. So since we are just looking at half the journey, time equals half the total time. Since we were provided 3.2 seconds, half of that is 1.6 seconds. We know the acceleration due to gravity, since this is a vertical motion problem, is going to be negative 9.8 meters per second squared. Final velocity in this half of the object's motion is 0. That is a known value if we focus on it that way. Initial position is also 0 since we're launching from the ground level. Initial velocity is what we're trying to figure out, as well as the maximum height. So the height at the apex and this initial velocity at launch. So we have two values to solve for here. Based on what we have listed so far, we're going to decide which equation we should use. So first, let's ignore the height question, and we're going to solve for initial velocity first. So based on the given variables, we have enough to use the first kinematics equation, which is final velocity equals initial velocity plus acceleration times time. We have final velocity, we have initial position, we have time, and acceleration listed as variables. All we're left is to solve for initial velocity. There's no mention of position for the first part of this problem. Once we know which equation we're using, we'll solve for the missing variable without numbers first, meaning do that algebraic rearrangement, use the inverse operations or the inverse operation to move things around so that you can make the equation equal to initial velocity. So since final velocity equals to 0, that's something that cancels out there. Subtract AT from both sides to isolate initial velocity. And then you can rewrite it with initial velocity on the left there. So once you do that, and you know which version of the equation you'll be using, put in your numbers, and what you'll end up with, make sure you note that there's a negative sign here. So that negative sign here is multiplied with the negative sign of acceleration. And remember, a negative times a negative is a positive. And then you also multiply by the 1.6 seconds. Once you multiply that all out, you end up with an initial velocity or a launch velocity of 15.7 meters per second. And we rounded to 3 digits in this case. Now we need to go back to the second part of the problem. So the first part of the problem was figuring out initial velocity, but we still need to know the maximum height. So now we can add in the known value of 15.7 meters per second, but we still need to figure out what the height is, the height at the apex or the final height. So now that we have these values, we have either of the remaining kinematics equations could be used. Now it's easier to use the first one listed here since it's already solved for x. So since we're looking for x, and this one is already equal to x, it's easiest to just go ahead and use it. So again, you want to solve for the missing variables without numbers. So do that algebraic rearrangement and then put in the numbers to solve for a numerical answer and check that you have the right units. So you put in all the numbers. It's already arranged in the correct arrangement for you, so no algebraic rearrangement needed. So you put in all the known values at this point. What you end up with is about 12.6 meters as the height at the apex of this object's path. Okay, let's try some practice problems. So an arrow is projected by a bow vertically up with a velocity of 40 meters per second and reaches a target in 3 seconds. How high is the target located? The correct answer for this problem is 75.9 meters. So it looks like we are using the position time equation. You can cancel anything that you know is equal to 0, which in this case is the initial position since you are shooting from the ground height. So that leaves you with this part of the equation to use, and it's already arranged, it's already solving for height, the final position. So you can just put in the numbers and you end up with 75.9 meters. Second question, an object accelerates from rest with a constant acceleration of 8.4 meters per second squared. What will its velocity be after 11 seconds? So for this one, the knowns that we are provided with lead us to using the first kinematics equation. So we have initial velocity. So we have acceleration from rest, which means initial velocity is 0. And then you have values for everything else, acceleration and time, which gives you a final velocity of 92.4 meters per second. And then the final question, an object accelerates from rest to a velocity of 34 meters per second over a distance of 70 meters. What was its acceleration? What we know from this problem, we'll be using the velocity position equation. Now, this one has already been rewritten for you, but this equation, recall, is originally written out as final velocity equals initial velocity plus 2 times acceleration times final position minus initial position. And you want to solve for acceleration. Now we know that we're accelerating from rest, so that initial velocity is going to be 0. Final velocity we know. We know that initial position is going to start from 0 since we're accelerating from rest. And we're provided final position, which is 70 meters. So since we want to solve for acceleration here, equals 2ax. So to solve for acceleration, we're just going to divide by 2x on both sides, which gives you acceleration equals final velocity squared divided by 2x. This says d. Sometimes you might see equations written where it says d instead of x, but we're using x. I just wanted to rewrite that so that you could see that based on what we've been using in class. So that would be the equation you use to solve this problem. Once you put in the numbers, so we have 34 meters per second, and then you have to square it, don't forget, divided by 2 times 70 meters, you end up with the acceleration of 8.26 meters per second squared. Now the classwork problems that go along with this, the chapter problems as in total, starting with number 59 through 76, those would be all of the mixed kinematics equations problems. If you have trouble with those, let me know so we can go over them in class.